Out of the morning sea mist, a colossal silhouette materializes. It moves with a silent, mechanical momentum that feels closer to geology than engineering. This is a steel structure stretching 400 meters from bow to stern, carrying hundreds of thousands of tons of mass through ocean swells, with total indifference to the weather. Approximately 90% of all non-bulk global goods travel inside these boxes. Every smartphone, winter coat, and medical device on your desk has a staggering probability of having crossed an ocean inside one of these sealed steel units. Without them, global store shelves would empty within weeks. Before the mid-20th century, general cargo was handled as break bulk, individual sacks, barrels, and wooden crates lifted manually into the hold. A vessel would routinely spend more time tied up in port, being loaded and unloaded, than it actually spent crossing the ocean. The port acted as a massive bottleneck that strangled the reach of global trade. That bottleneck broke on the 26th of April, 1956. Malcolm McLean, a trucking magnate tired of watching longshoremen take days to manually load cargo he could have driven across a state in hours, sent a converted World War II tanker called the SS Ideal X out of New Jersey. She carried 58 standardized metal containers on her deck. 5 days later, they were unloaded in Houston in under 8 hours. McLean had realized that the actual cargo needed to be invisible to the system. By standardizing the exterior box, he enabled intermodal transit, the ability to transfer goods seamlessly between a ship, a train, and a truck, without ever unpacking the contents. A crane does not care if it is lifting televisions or car parts. It only interacts with the exterior dimensions of the steel rectangle. Standardizing the box dropped cargo handling costs by an order of magnitude. Shipping evolved from an unpredictable, labor-intensive human craft into a mechanical system that could be optimized, automated, and scaled without limit. Today, that scale is measured in a universal metric, the TEU, or 20-foot equivalent unit. It represents the exact volume of a standard 20-foot-long container. Every crane, every port, and every commercial vessel on Earth is engineered around the strict dimensions of this specific box. This structural diagram of a container ship's cellular hold illustrates how that geometry dictates the vessel's architecture. Below deck, the cargo space is divided into individual cells by vertical steel guide rails. The containers drop exactly into position, held rigidly by the rails themselves. Above deck, they stack and lock together using a twist lock, a forged steel mechanism that rotates a quarter turn to fuse one container to the next. Tracking 20,000 identical boxes requires the bay, row, tier coordinate system. As shown here, it is a three-dimensional numerical grid, assigning every slot a unique address, a bay number along the length, a row across the width, and a tier up from the keel. A planner in Singapore can retrieve a single box from a tower and stack using nothing more than those three numbers. For decades, the geometry of these ships was constrained by planetary geography. The Panamax class was built to a maximum width of exactly 32.31 meters, specifically engineered to slide through the original locks of the Panama Canal with only inches to spare. The dimensions of a canal in Central America became the physical law governing global shipping. But as global trade volumes exploded, naval architects deliberately abandoned those limits to chase pure economies of scale. They built the ultra-large container vessel. These behemoths span widths of over 60 meters and lengths of 400 meters, capable of carrying up to 24,000 TEU on a single voyage. These ships bypass older canals entirely. Their design has decoupled from human scale proportions, governed instead by the ruthless, geometric pursuit of maximum container capacity. While the boxes are identical on the outside, their interiors hide a massive diversity of cargo. You'll find standard dry goods next to active reefers, highly insulated containers with their own electrical cooling units, preserving frozen salmon or temperature-sensitive pharmaceuticals. You'll even find flexivacs, massive polyethylene liners that convert a standard dry box into a transport mechanism for 26,000 liters of bulk liquid. A ship carrying goods only generates revenue when moving at sea. Every hour tied up at a berth is a cost, not an income. Therefore, the modern container terminal is engineered with a single aggressive directive: move as many boxes between water and land as physically possible in the absolute minimum amount of time. To achieve this velocity, massive ship-to-shore gantry cranes reach out over the vessel's beam, plucking 40-ton boxes from the hold in under 2 minutes. They drop them onto automated guided vehicles, driverless electric platforms that instantly route the box into dense storage yards. Orchestrating this entire mechanical ballet is the Terminal Operating System, or TOS. It is the central intelligence of the port. The software calculates the ship's stability plan, assigns yard coordinates, sequences the cranes, and tracks every moving vehicle simultaneously. At Shanghai's Yangshan Phase 4 terminal, this technology reaches its apex. Powered by digital twin modeling and big data analytics, the facility operates with automated rail-mounted cranes and driverless vehicles. During normal operations, there are almost no human beings on the ground. The modern port functions as a hyper-engineered, algorithmic logistics processor. Physical friction in the supply chain has been practically engineered out of existence. But that extreme efficiency hides a fatal vulnerability: schedule integrity. These ships operate like maritime buses on rigid, predetermined loops, calling at a sequence of ports exactly on timetable. They do not have the flexibility to wait for better conditions or rates. When a ship experiences a minor delay, a broken crane, or heavy fog, the disruption cascades forward. The vessel arrives late to its next port, missing its designated berth window, delaying the ship behind it, compounding the disruption exponentially through every subsequent stop in the rotation. We saw this systemic breakdown at scale during the 2021 supply chain crisis. Explosive consumer demand collided with reduced terminal productivity, overwhelming the inland logistics network. Dozens of ships were forced to drop anchor outside Los Angeles and Long Beach for weeks, waiting for terminal space that simply did not exist. This congestion is aggravated by container imbalance. Asia exports vastly more manufactured goods to Europe and North America than it imports. As a result, shipping lines must absorb the massive cost of repositioning millions of empty steel boxes backward across the ocean just to get the units back to the factories. Large container vessels are also susceptible to parametric rolling, a resonance condition causing the ship to swing violently up to 40 degrees, even in moderate seas. The dynamic forces generated can exceed the limits of the lashing rods, collapsing towering stacks of steel and sending thousands of tons of cargo into the sea. The industry's relentless drive to optimize cargo handling removed all the slack from the system. In extracting maximum speed, the global maritime network became a high-wire act of interlocking dependency, sensitive to the slightest disruption. In March 2021, that spring snapped. Caught in a sudden sandstorm, the Ever Given, a 400-meter-long ultra-large container vessel, lost steerage and ran aground. She wedged herself diagonally across both banks of the Suez Canal, completely sealing off the waterway. For 6 days, the route connecting the manufacturing hubs of Asia to the consuming economies of Europe was closed. That single blockage halted 12% of all global trade, delaying an estimated $9 billion of cargo value every single day. Humanity's most massive engineering achievements, mechanical systems of algorithmic cranes and automated leviathans, were brought to a total standstill by a single gust of wind and a sandbank. Pacing slows, resolving. Despite the fragility of the network, the moment a fully loaded ship casts off her lines, the terminal immediately resets. The cranes swing back to neutral. The automated vehicles reposition. It prepares for the next arrival.